Magnetic fields are produced due to wires that have currents in them. So it's not going to be as easy as it was when we're talking about Coulomb's law to get the electric field due to a point charge. You just simply had a point charge and you got the electric field. It was kq over r squared r hat. And the electric field lines went radially outward from the charge. In this case, it's very different. So we have a law that's similar to Coulomb's law in the sense that it has a 1 over r squared dependence, but it's much more complicated in the sense that to get the magnetic field due to a wire, you first have to know how to get the magnetic field due to an element of current, and then once you know that, then we can integrate that to get the magnetic field due to the whole wire. What we're showing here is just a segment of wire, a small piece. Of course, a small piece of wire can't just start from nowhere and go to nowhere. It must be a part of a continuous circuit, but we're not showing the continuous circuit. We're just showing a small element of the wire. And the element of the wire is placed at the origin, and the current going through the wire is I, and ds is an element of length. It points from the beginning of the element to the end of the element in the direction of the current. That's what ds is. Now, if you want to find the magnetic field, say at this point, then you have to define something called a unit vector r hat that points from the element of length to the point where you want to find the magnetic field. So that's what r hat is. And then r is the distance between the element of length and the point where you want to find the magnetic field. So this rule, Biot-Savart law, has the 1 over r squared dependence, similar to the case where we got for the electric field, but it's different in the numerator. You have this cross product between ds and r hat, and this makes it much more complicated. So dB is the magnetic field due to this small current element only. Remember that this small current element just can't appear from nowhere. It must be part of a continuous circuit, but we didn't show the rest of the circuit here. Mu node is just a constant. It's called the permittivity of free space. For our purposes, it's just a constant that has this value. So how would we use this rule to get the magnetic field due to different current distributions? That's what this chapter is about, the first part of the chapter. And we'll start by giving some intuitive feeling of how this cross product leads to magnetic fields, what the direction the magnetic fields would be for various positions. So first, let's focus on this position right here, on the negative part of the y-axis, and the ds is along the x-axis. R hat points from the origin to the point where we want to find the magnetic field. And let's ask the question, what would the direction of the magnetic field be at this point due to this current element only? So the direction of this vector, the direction of this vector. The direction of this vector is given by the direction of ds cross r hat, because I is just a constant, mu node is a constant, 4 pi is a constant, r squared is a constant. I mean, it's a number. It's a number. For this particular point, it's a number. So the thing that gives the direction is ds cross r hat. So if you put your fingers in the direction of ds and you curl towards r hat, the direction of the cross product will be pointing in the minus z hat, like that. So this vector represents the magnetic field vector at this point due to only this current element, infinitesimal current element. So this kind of gives us, going to give us an idea how the magnetic field looks like, how an element of current makes a magnetic field in the region around it. What if we ask for the magnetic field at this point? Well, at this point, the ds is the same because the current element is the same current element. But now the r hat unit vector has to point from the element to the new point that we're talking about. So now the r hat vector points in the minus z direction. And if you get now ds cross r hat, you put your finger in the direction of ds and you curl towards r hat, the direction of the cross product will be in the positive y direction. And now we go to this point over here. What will the magnetic field at this point be? Again, ds is the same. The difference is that r hat has changed. Now, since we want to find the magnetic field here, the r hat unit vector points from the element to the point, and it points in the positive y direction. So what would the magnetic field be? What would the direction of ds cross r hat be in this case? It'll be pointing in the k hat direction. And the same thing we can ask for this point. And you get this vector that points in the minus j hat direction. Let's put all of them together at the same time. So you can see here that an element of current doesn't produce a magnetic field going out radially the way a point charge would. It's completely different. The character is completely different. In fact, the magnetic field is going around in circles, around this element of current going around in circles. We got it now at 4 different points, but if you get it anywhere else, you can show that it goes around in circles. So if you look at the problem from along the x-axis, so remember the current element is along the x-axis, pointing in the positive x direction, coming out of the page. So here the element of current is here and it's coming out of the page. And this is what the magnetic field would look like at different points that we've chosen. As you go further and further away, the magnitude of the magnetic field gets weaker because of this 1 over r squared dependence. The direction is the same here and here and here, but it gets weaker and weaker as you go away. So this kind of shows you the influence of an element of current, what it looks like, at least in the plane perpendicular to the element of current. Of course, to get it at other locations, it would be much more complicated. So we're just looking at the magnetic field due to this element of current in the plane perpendicular to the element. Since the magnetic field is stronger when you get close to the element of current and it gets weaker when you go away, then if you draw magnetic field lines, the magnetic field lines will be closer to each other when you're close to the element of current, and they get farther and farther apart when you go farther and farther away. So this would be what the magnetic field would look like if you want to draw it in terms of magnetic field lines.